This video is in continuation of the previous video in which we were discussing projections on a Hilbert space H. So now we define an invariant closed linear space. So firstly, let we have an operator T on a Hilbert space H, and we have say closed linear subspace M of H. Then M is said to be invariant under T if T of M is contained in M. So we can say, as we can see from the name of invariant, that T of M is contained in M, means every vector of M has its image under T again in M. So when this type of situation happens, that means if T M is contained in M, then we can regard this operator T, we can regard the restriction of this operator T to be the operator on M alone. That means in this type of situation we can write, if we restrict T to M, then it will be an operator on M only, means it is an operator from M to M, because T of M is contained in M. So when we restrict it to M, then every image vector is contained in M. If both M and M perp are invariant under T, then we say that M reduces T. So if both M and M perp are invariant under T, so if both are invariant under T, that means T of M is contained in M and T of M perp is contained in M perp, then we say M reduces T. So this type of situation is very interesting. In this situation, we can replace the study of T as a whole by the study of its restrictions to M and M perp, because in this case actually T of M is contained in M and T of M perp is contained in M. That means both the restrictions, T restricted to M and T restriction to M perp, they are operators on M and M perp respectively. So the study for the operator T regarded as an operator on the whole of the Hilbert space H, that is replaced by the study of the operator T on M and operator T on M perp. So we translate these concepts into relations between T and the projections on M. So we will prove this theorem B. In this theorem, a closed linear subspace M is invariant under operator T if and only if its perp M perp is invariant under its the adjoint of the operator T, that is T star. So here we will prove a closed linear subspace M, obviously of Hilbert space H, Hilbert space M of Hilbert space H. This is invariant under T if and only if M perp is invariant under T star. So this is the relation between T and projection on M, or we can say this is the relation between the operator T and T star, T on M and T star on M perp. Now firstly we assume M is invariant under T. Firstly, we assume M is invariant under T, and we have to prove M perp is invariant under T star. So if M is invariant under T, that means T of M is contained in M. That means for any vector x in M, T of x is also in M. Now we want to prove M perp is invariant under T star. That means we want to prove T star of M perp. This is contained in M perp. That means for any vector y in M perp, we want to prove T star y is contained in M perp. So let y belongs to M perp, any vector. So we want to prove that T star y belongs to M perp. Now we want to prove T star y belongs to M perp. That means we want to prove the inner product of T star y with any vector of M is 0. So let us start from this x and T star y for any x in M. For any x in M, we start from this x T star y. So by definition it is Txy. Now x belongs to M and y belongs to M perp. And secondly, we know Tm is contained in M. Now because x belongs to M, so Tx is also in M. So Tx belongs to M and this y belongs to M perp. So this is 0 because x belongs to M implies Tx belongs to M and y belongs to M perp. So these two vectors, they belong to M and M perp respectively, so their inner product is 0. So we have proved for any x in M, x and T star y, their inner product is 0. It means T star y belongs to M perp. So now we have proved for any y in M perp, T star y is an M perp. That means M perp is invariant under T star. So now we will prove the converse. Converse is just similar. If M perp is invariant under T star, then we want to prove M is invariant under T. If M perp is invariant under T star, it means T star of M perp, this is contained in M perp, and we want to prove M is invariant under T. That means we want to prove Tm is contained in M. So let any x belongs to M. So we want to prove Tx belongs to M. Now Txy for any y in M perp, Txy, this inner product is x T star y. Now because y belongs to M perp and T star of M perp is contained in M perp, this means T star y is also in M perp. So x belongs to M, so this inner product is 0. So this is 0 for any y in M perp and x in M. This means Tx belongs to M perp of perp, which means M. M perp of M is M, just M. So Tx belongs to M. If Tx belongs to M, it means Tm is contained in M. That means M is invariant under T. Now we have next theorem, which is actually consequence of the previous theorem, which says a closed linear subspace M, a closed linear subspace M of H reduces operator T. Reduces means if M and M perp both are invariant under T. So if it reduces the subspace M, if and only if M is invariant under T and T star both. So by the condition linear subspace M reduces T, by definition we have T is reduced by M and M perp both. If T is reduced by M, then T star is reduced by M perp. So by the previous theorem, this theorem is obvious. So we have next theorem, theorem D. If P is projection on a closed linear subspace M of H, if P is projection on a closed linear subspace M of H, then M is invariant under operator T if and only if Tp is equal to P Tp. If and only if Tp is Ptp. If M is invariant under T, then we have to prove Tp is equal to Ptp. So let firstly M be invariant under T. So here we have given that P is a projection on closed linear subspace M. If P is projection on M, then range space of P is M. So for any arbitrary vector x in H, T of Px, this belongs to M, because for any x in H, Px belongs to M and M is invariant under T, so T of Px is also in M. Now since P is projection, so Px belongs to M, and since M is invariant under T, so T of Px is in M. It means P of Tpx, that is equal to just Tpx, because Tpx belongs to M, and for any vector in M, P of that vector is just the same vector. So it means P of Tp is Tp. So conversely, if we have Tp is equal to Ptp, we want to prove M is invariant under T. That means we want to prove for any vector x in M, Tx is also in M. So let x belongs to M. We want to prove Tx is also in M. Now Tx is equal to T of Px, because P is projection on M and x belongs to M. Now T of Px, because this is given to us, T of P is equal to P of Tp, so it is P of Tpx. Now P of something, so it is P of Tpx. So P of anything that belongs to M, because M is range space of P, therefore Tx belongs to M for any x in M, therefore M is invariant under T. Next theorem says if P is a projection on a closed linear subspace, then M reduces that operator if and only if T and P commute with each other. So in the previous theorem we have proved M is invariant under operator T if and only if Tp is equal to Ptp. But in this theorem we will prove that M reduces an operator, which means M and M perp both are invariant under the operator T if T and P commute with each other. So again P is projection on closed linear subspace M of H, then M reduces T if and only if Tp is equal to Pt. So from previous theorem, M reduces T. Let us say M reduces T. Now we have to prove Tp is equal to Pt. So by definition, M reduces T, or by the theorem C, M reduces T if and only if M is invariant under both T and T star. So from the previous theorem, if M is invariant under T, that means Tp is equal to Ptp, and M is invariant under T star, it means T star P is equal to Pt star P. So if and only if these two conditions are same. Now P is a projection, so P star is equal to P, which means P is self-adjoint operator. So taking the adjoint of these two, we will get if and only if this is P star T, this is P star T, P star, because P is projection, so P star is equal to P, so it is Pt, Pt, P, because P star is equal to P. Now from these two we can say Pt is equal to Tp. So next theorem shows how projections can be used to express the statement that any two closed linear subspaces of H are orthogonal. So let us say two projections P and Q. These are projections on closed linear subspaces M and N respectively. Of the Hilbert space H. Then M is perpendicular to N if and only if PQ is 0, if and only if QP is 0. So firstly, PQ is 0 and QP is equal to 0. These statements are equivalent to each other since both are projections, and one statement can be obtained from the other by taking adjoints. For example, PQ is 0 if and only if PQ star is 0, if and only if Q star P star is 0, so if and only if QP is 0, because Q and P both are projections, therefore P star is equal to P and Q star is equal to Q. So these two conditions are equivalent to each other. Now we will prove that M is perpendicular to N if and only if PQ is 0. So firstly we assume M is perpendicular to N. If M is perpendicular to N, then N is contained in M perp. Then we have to prove PQ is equal to 0. That means we want to prove for any x in H, PQ of x is H. So let any x in H, we want to prove PQ of x is 0. Now for any x in H, since Q is projection on the linear space N, so Q of x belongs to N. Because Q is projection on N means the range space of Q is N. So every vector Qx belongs to N. Now since Qx belongs to N and N is contained in M perp, so P of Qx, that is 0, because N is contained in M perp. So this vector Qx belongs to N, that means Qx belongs to M perp, and we know P is a projection on linear space M, that means the null space of P is M perp. So if some vector belongs to M perp, then P of that vector is 0. So P of X is 0, it means PQ is 0. Now conversely, if PQ is 0, we want to prove M is perpendicular to N. So if PQ is 0, then for any X in N, let X in N, Px is equal to Pqx, because if X belongs to N, then Qx is X, because Q is a projection on N, so for any vector in N, Qx is X. So P of X is PQX, but PQ is given to us 0, so PQ of X is 0. So now we have proved that for any X in N, P of X is 0, but we know P is a projection on M, so it means this X belongs to the null space of P, and null space of P is M perp, so N is contained in M perp, and N is contained in M perp means N is perpendicular to M. So this completes the proof of the theorem. Now because we have this result that M is invariant under we have this result if M is perpendicular to N, then PQ and QP are 0 whenever P and Q are projections on closed linear subspaces M and N. So we define two projections are orthogonal if PQ is 0. So we define this thing, two projections P and Q are orthogonal. Obviously these two are, if they are projections, then they are projections on some subspace of the Hilbert space H. So two projections are orthogonal if their product is 0, or we can say in the view of the previous theorem that two projections are orthogonal if their range spaces are orthogonal to each other. Now we have the last theorem of this section, which says which describes the circumstances under which a sum of projections is also a projections. So let us see when a sum of projections is again a projection. So now we have P1, P2, Pn. Let us say these are projections on closed linear subspaces M1, M2, Mn. These are projections on closed linear subspaces M1, M2, Mn of H. Then we want to prove that their sum P1, P2, P3 up to Pn, this is a projection if and only if all these Pi's are pairwise orthogonal. So what it means, pairwise orthogonal? It means Pi, Pj is 0 whenever I and j, they are different subscripts. And moreover, in this case, we want to prove that P is projection on M, and here this M is just the sum of all the subspaces M1, M2, Mn. So firstly we prove here that sum of the projections P1, P2, Pn, that is P, this is a projection if and only if all Pi's are orthogonal, pairwise orthogonal. So firstly we are given this, that all these Pi's are projections on some closed linear subspaces M1, M2, Mn. That means all these Pi's, they are self-adjoint operators and idempotent operators. So if they are self-adjoint, now since Pi's are projections, therefore Pi's are self-adjoint. It means Pi star is equal to Pi for all I. Now we want to prove P is also self-adjoint. So P star is just P1 plus P2 up to Pn, this is star, and this is just P1 star, P2 star up to Pn star. But because all of these are self-adjoint, So ultimately they are just sum of p1 p2 pn, and that is p. So p star is equal to p, so p is self adjoint. This thing is true always, but we have to prove this p is actually a projection if and only if pi's are pairwise orthogonal. So we will prove here only that p is idempotent if and only if pi's are pairwise orthogonal. So firstly we assume p is projection. If p is projection, that means firstly we assume p is projection, that is p is idempotent, and we want to prove pi's are pairwise orthogonal. Now if P is idempotent and we want to prove PI's are pairwise orthogonal, so for this let me start from X, where X be a vector in the range of Pi. Let X be a vector in range of Pi. If this is in the range of Pi, then Pix is equal to X. Then we start with norm of X square. Now because x is equal to pix, so it is norm of pix square. Now this will be less than equals to norm of pjx for all j varying from 1 to n, because norm are non-negative quantities. So this one quantity is less than equals to these n sum of n quantities. And now we know this norm square, this can be written just pjx from 1 to n. So this is just summation pjx and summation pjx. So this is px because p is sum p1 p2 pn. Now px is norm of px square, and norm of px square is less than equals to norm x square. Now norm of px square is less than equals to norm x square. This is because we have proved earlier that if p is a projection, then p is lying between 0 and I. That means norm of p is less than equals to 1, because norm of I is 1, so norm of p is less than equals to 1. So norm of p is less than equals to 1, it means norm of px square is less than equals to norm x square. So now we have proved here norm of x square is less than equals to this quantity, and this is further less than equals to norm of x square. That means all the quantities in this inequality, they are equal, because left hand side and right hand side are same. So therefore we can say here that this summation is actually equal to this norm. So summation pjx square is equal to norm pix square. This is 1 to n. So it means norm of pjx, this is 0 for all j not equal to I, because here we are taking sum from 1 to n, and here we are taking only ith term. So if this sum is equal to just the ith term, that means all other terms in the summation, they are 0. So it means pjx is 0 whenever j is not equal to I. It means pjx is 0 for all j not equal to I. So we have assumed here x x is a vector in the range of pi, and we have proved pjx is 0 for all j not equal to I. That means if for any vector x in the range of pi, that x belongs to null space of pj. So any vector x which lies in the range of pi is contained in null space of pj, and we know null space of pj is just mj perp. So it means mi is contained in mj perp for all j not equal to I. It means mi is perpendicular to mj for all not j equal to I. So from the definition, now we have defined here two projections P and Q are orthogonal if PQ is 0. That means if range of P and range of Q, they are orthogonal to each other. So now we have proved range of Pi and range of Pj are orthogonal. That means Pi, Pj, that is 0 for all j not equal to I. That means Pi, Pj, Pi's are pairwise orthogonal. So therefore we can write Pi's are pairwise orthogonal. Now conversely, we want to prove if Pi's are pairwise orthogonal, then P is idempotent, and that is obvious. To prove P is idempotent, we have to prove P square is equal to P. So let us start from P square. That will be just this square. So this square contains P1 square, P2 square up to Pn square plus twice of the factors of the type P1, P2 and so on up to Pn minus 1 Pn. Means summation of Pi, Pj whenever j is not equal to I. So because Pi's are pairwise orthogonal, so all these factors are 0, so it will be left only P1 square up to Pn square, and we know all these are projections, so they are idempotent, so their squares are equal to just the projections, so this is equal to P. So P square is equal to P means P is idempotent and it is self-adjoint operator always, so it is projection. Now moreover we have to prove if this thing holds, then this P is actually a projection on M, where M is sum of all the spaces M1, M2, Mn. Now we want to prove P is projection on M, where M is this M1 plus up to Mn. Now firstly we observe from this statement that because we have proved that all these factors they are equal in this inequality, so we have norm of Px is equal to x from here. So we have observed in that inequality that norm of Px is equal to norm of x for every x in Mi. Whenever x belongs to Mi, norm of Px is equal to norm of x. And we have earlier proved a theorem, if x belongs to M, where M is range space of a projection P, then x belongs to M if and only if norm of Px is equal to norm of x. So now norm of Px is equal to norm of x, it means x belongs to range of projection P. So x belongs to range of P. So here we are proving that whenever x belongs to Mi, norm of Px is equal to norm of x, and because of this equality x belongs to range of P. That means Mi is contained in range of P. So Mi is contained in range of P, and this thing is obvious for each I. This thing is true for each I. So Mi is contained in range of P for each I. It means M is contained in range of P, because M is sum of all the Mi's, and all the Mi's are contained in range space of P. So M is contained in range of P. Secondly, if x belongs to range of P, x is any vector in the range of P, then x is equal to Px, because P is a projection, and P is just P1, P2, sum of P1, P2, Pn. So it is P1x, P2x and Pnx. Now this P1x belongs to M1, because for any x in H, P1x belongs to M1, since M1 is range space of P1. Similarly, P2x belongs to M2 and so on. Pnx belongs to Mn. So this sum belongs to the sum M1 plus up to Mn, and this is just M. So we have proved here two things, that M is contained in range of P, and in the second we are starting with x, which is in the range of p, and we have proved that x belongs to M. That means here we can say range of p is contained in M. So from this and this we can say M is equal to range of P. If M is range of P and P is a projection, that means P is projection on M. And this completes the proof of this section as well as the chapter.